This lecture is about polynomials. So, what is a polynomial? Let's start with the definition. In order to define a polynomial, let's first define what a term is. So a term is a product, remember product means multiplication, of constants being numbers, and or variables. Variables we normally represent with letters. So for example, the number 2 is a term. Negative 3xy cubed is a term. 24x squared is a term. These are all products of constants and variables. So a polynomial is just a sum of terms. Add a bunch of terms together. And so, for example, some examples of some polynomials. Negative 2 is a polynomial. It's a polynomial with a single term. 3x squared minus 9 is a polynomial. It's a polynomial that has two terms. Notice we write minus 9, but this is really something that can be written as 3x squared plus negative 9, so it's a sum of two terms, even though it's written as subtraction. 4a squared b plus 2c plus 3c to the fourth power. Here's a polynomial with three terms. Y squared minus xz, that's a polynomial with two terms. Again, it's written as subtraction, but we can always rewrite subtraction as addition with a negative number, so that is a polynomial. It's a sum of two terms. So, why are we interested in polynomials? Well, one of the major reasons we study polynomials is because polynomials can often be used to model real-world phenomena. For example, the position or speed of a falling object can be modeled by polynomials. For example, the volume and area of rectangular solids. Rectangular solids meaning things like squares, rectangles, cubes, etc. And often more complex equations, like for example, if I had a graph that looks something like this, I can actually approximate that with polynomials. So polynomials can often be used to approximate more complex equations or graphs. Okay, so what do we want to be able to do with polynomials? several things. We want to be able to simplify them. We want to be able to perform operations on them, such as addition, subtraction, multiplication, and we're not going to talk about this in this lecture, but also division. So we want to be able to add two polynomials, multiply two polynomials, etc. We want to be able to factor them. We're not going to do that in this lecture. This will come up in the next lecture. Factoring is just the opposite of multiplying. We go backwards. Instead of multiplying two things together and to get an answer, to get a product, we start with the product and go backwards to find out what the factors were. And then at some point we'll also want to solve equations containing polynomials. Although we won't cover that in this lecture. So this lecture in particular will focus on simplifying them and performing addition, subtraction, and multiplication. So let's start with simplifying polynomials. Before we start talking about how to simplify polynomials precisely, I want to make a couple of notes that will be important. First of all, as we've already mentioned, subtraction can always be rewritten as addition with a negative number. So for example, a minus b can be rewritten as a plus negative b. Or if you prefer, you can write it as a plus and put the negative b in parentheses to make it even clearer that the negative sign goes with the b. Another note we want to make is that you'll notice that the order in which we add things does not matter. As long as it's all addition, we can rearrange the terms in whatever way we want. So this means that we can rearrange terms in a polynomial into whatever order we want without changing the polynomial. Right, simple example we'd see is a plus b obviously equals b plus a. Because when we're adding things, we're just putting them all together. So if I have two things and I throw them into a box, and I have five more things and I throw them into a box, it doesn't matter whether I put the two things in first or the five things in first, I'm going to end up with seven things at the end anyway. Because that's basically what addition is. It's like collecting everything all together and then counting up what you've got at the end. Okay, so how do we simplify polynomials? Well, the real question is, when can we combine two terms that's in a polynomial together into a single term? We can move everything around into a polynomial into whatever order we want, because we know we can rewrite all the subtraction as addition, and then once it's all addition, we can reorder it in any way. So the only question we need to answer in order to simplify polynomials then is to ask ourselves, once we've rearranged the terms, when can we combine two or more terms together? Well, the short answer to that is when the variable part is the same we can combine coefficients. So let's look at some examples. For example, 3x squared minus 5x squared. We could rewrite this as addition, so this is really 3x squared plus negative 5x squared. We can see that the variable part is the same. Here's the variable part, is the x squared and the x squared. These are the same. The coefficient parts, which are 3 and negative 5, can then be added. So we get 3 plus negative 5 times the variable part, which is x squared. So we will get in total negative 2x squared. Now this makes sense. When we think about it, what is that coefficient really telling us? This coefficient is telling us that we've got 3x squareds. This coefficient is telling us that we've got negative 5x squareds. So how many x squareds do we have altogether? Well, we have 3 plus negative 5x squareds altogether. So notice when we add them together, we only add the coefficients. The variable part stays the same, because that's the thing we're counting. The coefficient is telling us how many we're counting up, and the variable part is telling us what we're counting. Let's look at another example. 4y squared minus 2y. Here the variable part is y squared. Here the variable part is y. Y squared does not equal y. They're different. While they both have a y in them, y squared is not the same thing as y. Just like 2 squared is not the same thing as 2. 2 squared is 4. They're not equal. So because these are equal, these are not what we call like terms. In other words, they don't have the same variable part. The variable parts are different. Okay, let's continue with a few more examples. Let's look at this one. Here, the variable part is ab squared. The variable part is ab squared. These are the same. So we can add the two coefficients. So we get 4 plus 2 times ab squared. There's our variable part again. And so we get 6 ab squared. Again, we're just literally counting up how many ab squareds we have. We have 4 of them here. We have 2 of them here. So in total, we're going to end up with 6 of them. Let's take a look at another example. pq squared minus p squared q. If I look at the variable part, this is pq squared. This is p squared q. pq squared is not equal to p squared q, right? This is really p times q times q. This is really p times q. Notice these two things are not equal. This one has 2 q's and 1 p. This one has 2 p's and 1 q. So here, these are not like terms. In other words, the variable parts are not the same. The basic idea behind combining like terms is that we can only count up things if they're the same. If we have a bunch of things over here on the left that are the same type of thing, and a bunch of things over the right that are the same type of thing, we can count up how many of those things we have on the left, how many of them we have on the right, and put that total up together. But if we've got totally different things on the left than we do on the right, we can't combine them into one possible counting, because then we're not counting up the right sized things. For example, if I had really tiny pieces of pie over my right and I had whole pies over my left, it doesn't make sense to say I have 5 whole pies and 3 little tiny pieces of pie and to say I have 8 of something total, because the things are different sizes. I have 5 whole pies and I have 3 pieces. I have to keep them separate because the sizes of the things that I'm looking at are not the same. There's some actually more complex examples that we're not going to encounter in this lecture, but we're going to see them once we want to start factoring things. So I'm going to go ahead and mention these here while we look at it. Some more complex examples of what we call like terms. In other words, terms where the variable part is the same. Depends on how we define the variable part. We can actually be a little bit creative in how we define the variable part, so that the coefficient part could even have other variables in it. Let's look at some examples so you can kind of see what I mean. What if we had this? 2 times x minus y plus x times x minus y. This is a little sneaky, but you'll notice you could get creative here and say, well, if you count this as the variable part in both cases, it's the same. So this we could treat as the coefficient. It has a variable in it, but it's being multiplied by the variable part, so we could treat it like a coefficient. And in this case, what would happen? Well, we do just as we do before. We add the two coefficients, 2 plus x, and we multiply them times the variable part. Notice this is still the same. Right? In this first term, we had 2 x minus y's. In this second term, we had x many x minus y's. So here, what we end up with is 2 plus x many x minus y's. And so we could, in fact, rewrite it this way. Let's look at another example of these weird examples. Again, we're not going to encounter these that often, but when we need to factor things, we will see things that look like this, so we want to be comfortable with this. What if we have a squared times b squared minus 1 minus b times b squared minus 1? Well, again, if I treat the stuff in the parentheses as the variable part, you can see that it is equal. And if I treat this part as the coefficient, even though it contains a variable, and this part as the coefficient, again, even though it contains a variable, then I can do exactly what I've been doing in all the other problems. First, I need to rewrite this as subtraction, as addition. So I could say a squared b squared minus 1 plus negative b times b squared minus 1. And now I can just go ahead and add the two coefficients, a squared plus negative b times the variable part, b squared minus 1. So again, we notice The variable part stayed the same as it did in these first two terms, because that's the thing we're counting up. And then this came from adding the two coefficient parts. And you may also notice, so we could leave it here like this if we want. That's good. But if you prefer rewriting addition and subtraction when there are negative numbers there, you could also write it as a squared minus b times b squared minus 1. Either of these ways of writing it are equally good. It just depends on what your preferences are. So, we know how to simplify polynomials because we know that in order to simplify them, all we have to do is combine like terms. Let's go ahead and do an example briefly. What if we have 3y squared minus 2xy plus 1 minus y squared plus 7 minus 4xy. Well, the first thing we want to do is we want to rewrite this so that everything is addition. So 3y squared plus negative 2xy plus 1 plus negative y squared plus 7 plus negative 4xy. Now, because it's all addition, I can rearrange it whatever order I want. So I have a 3y squared here. Do I have any other y squared? So I've written that one down. That's not a y squared, that's not. But here I have another y squared. So I'm going to say plus negative y squared. Written that one down. That's not a y squared, that's not a y squared. So the next piece, the next term I have here is plus negative 2xy. Do I have any other xy's? That's not an xy, that's not xy. But here is a negative 4xy. So I've got that one written down. Now the next term that I have not yet written down is a plus 1. So I've written that down. And the last thing I have left is a plus 7. So I've written that down. I can see I have all 6 terms. I've just written them in a different order. Now, these two terms are like terms because they both have y squareds in them. So I'm going to get something y squared. And then these two terms are like terms because they both have xy's in them. The variable part is just xy. So I know I'm going to get something times xy. And these two terms are just numbers. So these I can even go ahead and add together. I know I'm just going to get 1 plus 7, which is 8. And so what am I adding together with the y squared? So I'm adding 3 plus that negative in front of the y squared is really a negative 1. Negative y squared is just the same thing as negative 1y squared. Because negative 1 times y squared is just negative y squared. Okay, xy's. The first coefficient is negative 2, and the second coefficient is negative 4, so I'm going to add negative 2 plus negative 4. That's going to tell me how many xy's total I have. So if I add these together, 3 plus negative 1 is negative 2y squared, plus negative 2 plus negative 4 is negative 6 xy, and then 8. So this is it. I have simplified my polynomial. I no longer have anything I can put together. I could also, if you prefer, to write all adding negatives as subtraction, I could write this as negative 2y squared minus 6xy plus 8. That would also be an acceptable answer. So we can see how to simplify polynomials. All we need to do is rewrite everything as all the subtraction as addition. And then we can rearrange the terms into whatever order we want. It makes sense to do that so that like terms are next to each other. And then we just combine like terms. And when we combine like terms, the main thing to be careful of is to be sure that we keep track of negative signs, that we add things correctly, and that when we write the product of our like terms, we're very careful that the variable part stays the same throughout the whole process. Okay, now that we know how to simplify polynomials, it's actually really easy to progress on to adding and subtracting polynomials. Since a polynomial is just the sum of a bunch of terms, adding two polynomials means you just add together two sums of terms. So you just still have a sum of terms. So adding two polynomials will give you a new polynomial. And since subtraction is just the same thing as addition, we can always rewrite it as addition as long as we're willing to use negative signs. The same thing holds true. When we add or subtract polynomials, we're just really getting one big polynomial. So let's look at an example here. Here's a polynomial, x squared minus 4. And let's add it together to 2x squared plus 6x minus 1. Well, we know that since these are both polynomials, we can rewrite them as totally just as addition. So we write the first one as x squared plus negative 4, and 2x squared plus 6x plus negative 1. Now, since this entire expression only contains addition between the terms, obviously the terms themselves have some multiplication in them, we can go ahead and rearrange those terms. We can regroup and rearrange the terms in any way that we want. Because again, when we're adding, we're just kind of counting up how many things we've got, so it doesn't matter which one we do first. So we can rewrite this as x squared plus negative 4 plus 2x squared plus 6x plus negative 1. And now I can reorder like terms so they're next to each other. So I have an x squared. I'm going to write that down. And I'm going to look for other x squareds. Here's a 2x squared, so I'm going to write that down. Now I have a 6x here, so I'm going to write that down. And then I have a negative 4, so I'm going to write that down, and a negative 1, so I'm going to write that down. So now I've got my x squareds together and my regular numbers together, so I can combine those two. X squared plus 2x squared, well, I'm going to end up with some x squareds where I just add the coefficients. The 6x doesn't have any other like terms, so that's the best we can do with it. And negative 4 plus negative 1 we know is negative 5. So what are the coefficients on these x squareds? Well, x squared is really 1 times x squared, so that's really a 1 as a coefficient. And we have a 2 on this one. So 1x squared plus 2x squared means we have 3x squareds total. So we get 3x squared plus 6x plus negative 5, or if we prefer, we can write it as 3x squared plus 6x minus 5. Either way of writing our answer is totally fine. They both mean the same thing. Let's do another example on a fresh page. Here's a polynomial, x squared minus 2x minus 6. And let's subtract a polynomial from this one. 2x squared plus 6x minus 9. Okay, again, first step here is let's change everything to addition, so there's only addition between the terms. Because if everything is addition, then we can regroup, rearrange it in whatever way we want. That allows us to combine like terms and simplify. So I will start by rewriting this. X squared plus negative 2x plus negative 6. Aha, and then here I've got a minus sign, so I can write this as plus negative 1 times, because you can imagine there's always a 1 in front, that doesn't change it, 2x squared plus 6x plus negative 9. Now that I've rewritten so that everything is just an addition sign between the various terms, I can get rid of the parentheses here. This is just x squared plus negative 2x plus negative 6. But I notice here I'm going to need to distribute this negative 1 before I can get rid of the parentheses. So I'll do that. Negative 1 times 2x is negative 1 times 2x squared is negative 2x squared. Negative 1 times 6x is negative 6x. And negative 1 times 9 is positive 9. Now that I've rewritten everything as just a sum of terms, I can reorder them. So I've got the things with squares in them are x squared and negative 2x squared. So these are like terms that I can combine. I can even write the x squared as 1x squared, so I can see my coefficient there. I have a negative 2x, so I'm going to write that. And I have a negative 6x, so I'm going to write that also. These are like terms, so they can be combined. And then I have a negative 6, and I have a positive 9. These are like terms, so they can be combined. So I have x squared terms here, so I'm going to add the coefficients in front of the x squared, which is 1 plus negative 2. Here I have like terms with an x in them, so I'm going to add the coefficients in front of the x's to get negative 2 plus negative 6. And here I've just got two regular numbers, so I can go ahead and add them. Negative 6 plus 9 is positive 3. So 1 plus negative 2 is negative 1, x squared. Negative 2 plus negative 6 is negative 8, x, plus 3. And then negative 1x squared I normally write as just negative x squared, although it could be written as negative 1x squared. That's not wrong. It's slightly simpler to write it this way. So I've simplified my expression after subtracting these two polynomials. If I prefer, I could also write it as the negative 8x as minus 8x, if I prefer. Let's look at one more example. Here's an example where I'm combining polynomials in a bunch of different ways. What if I have x minus 5, parentheses, 2x minus 3 minus x, close parentheses, close parentheses. Here, each of the pieces here, this is a polynomial here, 3 minus x. The 2x minus the 3 minus x is a polynomial. We can see this is a polynomial that's written in kind of a funny way in lots of different pieces. So here, again, just as usual, I'm going subtracting some polynomial bits and adding some polynomial bits. I'm going to rewrite everything as addition. So I get x plus negative 5, parentheses, 2x plus, and again I'm going to put a negative 1 there because it's like there's a 1 out front, 3 plus negative x. Remember, whenever we don't see a coefficient, we can always put a 1 there because 1 multiplied by anything doesn't change it. So what I'm going to get now, I want to start simplifying this. If you remember back from when you first talked about order of operations, I have to do things in a certain order, but it's kind of common sense. I would like to be able to multiply this negative 5 out to get rid of these parentheses, but if I start to do that, I'd have to multiply it times each piece, and I've got parentheses inside parentheses. That's kind of messy. So it makes sense to target first the parentheses that are on the inside to see if I can get rid of those first. So I'm going to copy the rest of this problem exactly as it is, because I haven't tackled any of it yet. But then I want to see if I can get rid of this set of parentheses here. Well, I can do that if I go ahead and distribute the negative 1. So this negative 1 I'm going to want to distribute. So I get negative 1 times 3 is negative 3. Negative 1 times negative x is positive x. And now I've gotten rid of those parentheses. And now I can simplify a bit what's inside the parentheses. I've got 2x and x, so I can put those next to each other because those are like terms. And now I can combine them. 2x plus x is going to be 2 plus 1 times x, because you can think of there being a 1 coefficient out there. And so I can rewrite that as 3x plus negative 3. Okay, now I'd like to get rid of this set of parentheses, which I can do if I distribute the negative 5 to both pieces. So I'm going to do that. Negative 5 times 3x is negative 15x. And negative 5 times negative 3 is positive 15. So I've just gotten rid of those parentheses by distributing the negative 5. And now in one last step, I need to combine these like terms here. Well, this is the same thing as 1x plus negative 15x. So I'm going to add the coefficients, 1 plus negative 15 times x. And I've still got this 15 here. 1 plus negative 15 is negative 14x plus 15. So that's my final answer. You'll notice in this example, I really wrote every single step out carefully. This problem is actually a pretty easy problem when you consider that each individual step is pretty simple. You just have to go through a lot of different steps to get to the answer. Now, not everybody writes out quite as many steps as I do here in this example, and you don't necessarily have to write out every single step that I've written out to get this correct. But I would recommend initially, when you're first starting, and if you find, even after you've practiced for a while, if you're getting some of them wrong because of small mistakes, the more steps you can write out very clearly in a nice, neatly lined up row like this, in a nice column, the less likely you are to make small mistakes where you lose negative signs, where you add things incorrectly, where you forget to distribute something to every single piece. So I would recommend trying doing a bit something similar like what I've done here, where I've really written out every step very carefully. And you notice in each step I wrote out even the pieces that weren't changing, because I didn't want to lose track of anything as I went. I wanted to be sure that the whole thing was written out in every step, so I knew exactly what I had. So I strongly recommend that you do that as you work on these problems. Okay, we've talked about adding and subtracting polynomials. The one major thing that leaves us to discuss in this lecture is how to multiply polynomials. Well, we already know how to do some multiplication, so let's go back and remind ourselves of a basic definition. You've known about something called the distributive property. In fact, we just used it in some of those problems that we've been doing in the last section. But let's write it out again. The distributive property is for any values a, x, and y, for example, a times x plus y is just equal to a times x plus a times y. Right? But this word distributive comes because we can think of kind of distributing the a to each piece inside the parentheses. In fact, if we want to write it out more generally, it could be fancy and even say for any values a, x1, x2, and so forth, xn, to any number n, a times x1 plus x2 plus x3 and so forth. We add a whole bunch of numbers, or a whole bunch of values, or a whole bunch of variable quantities here. We can still just distribute it to every single piece, no matter how many things we have. So we still just get a x1 plus a x2 plus a x3 plus ax to the n. Okay. The basic principle is, if we have multiplication, if we're trying to multiply a sum by a single number, we can go ahead and do the multiplication first if we make sure we do the multiplication to every single term in the sum. Now, let's look at some examples where we will try to multiply polynomials and see if we can use what we know about the distributive property to figure out exactly what we need to do in order to multiply polynomials together. Let's start with a simple example. Let's start with 2x squared times 3x squared plus 6x minus 1. Here, this is a polynomial with one term, we call it a monomial, and this is a polynomial with three terms, which we would call a trinomial. So if we want to think about how could we multiply these two polynomials together, well, in this case it's fairly simple. Because this is a monomial, or something with only one term, we can just use the distributive property. As long as we first rewrite this part so that it's all addition, then we can go ahead and distribute this to each piece. So let's do that. Let's first rewrite everything as addition. So the minus 1 becomes plus a negative 1. And then once we've done that, the distributive property works. We can just multiply this coefficient on the outside times each term on the inside of the parentheses. So I get 2x squared times 3x squared plus 2x squared times 6x plus 2x squared times negative 1. So let's look at each piece there. I can rearrange the stuff in this multiplication here, because this is all multiplication. 2 times x squared times 3 times x squared, so I can rewrite that as 2 times 3 times x squared times x squared. Same thing here, it's all multiplication, so I can rearrange it. I can say 2 times 6 times x squared times x, and here same thing, it's all multiplication, so I can rearrange it, so I can write 2 times negative 1 times x squared. And so now I can go ahead and do my multiplication. 2 times 3 is 6. X squared times x squared is like multiplying 2 x's by 2 more x's, so it's like multiplying 4 x's together total, so we get x to the 4th. We remember our adding the exponents pattern there. Here I have 2 times 6 is 12. X squared times x is like multiplying 2 x's and then another x, so I'm multiplying 3 x's altogether. Or x to the 2 times x to the 1 power, 2 plus 1 is 3. Here I have 2 times negative 1 is negative 2, and I already have the x squared, so I'm all set. This is simplified. If I want, I could also rewrite it so that I don't have any adding and negative, I just have some subtraction. Either one of these is fine. We don't need to write both, just one or the other. So here I've actually multiplied two polynomials. And all I had to do was use the distributive property. So that one was pretty simple. Let's try another one. So we know how to multiply a monomial by a polynomial, because we can just use the distributive property to do it. But what happens if we have a binomial, something with two terms? So let's pick something nice and simple. For example, x plus 2 times 3x minus 1. This is a binomial. In other words, it has two terms. So again, just as I did before, I'm going to start by writing everything out as addition, and then I'm going to stop and think, is there a way I can use the distributive property here? So here I've got x plus 2 times 3x plus negative 1. Alright, well, there is a way for me to use the distributive property here if I get a little creative. If I just treat this whole binomial as a single piece and distribute it to each piece in here, I could certainly do that. And if I did that, what would I get? If I did that, I would get x plus 2 times 3x plus x plus 2 times negative 1. I use the distributive property. That works. And now, if I look at what I have, notice, what do I have now? Well, I now have two places, here and here, where I'm multiplying a monomial times a polynomial. So you notice this is now a monomial. This is now a monomial. So what I have now is something where I can use the distributive property. It's written in the opposite order that I normally have the distributive property, but it still works. So now I can use the distributive property a second time to go ahead and finish multiplying all this out. I can say x times 3x plus 2 times 3x for that first piece, and now for the second piece, x times negative 1 plus 2 times negative 1. I just distributed the 3x to the x and to the 2, and then the negative 1 to the x, and then the 2. And so, just like before, I can go ahead and, because this is all multiplication, I can rewrite this as 3 times x times x. Here I still have 2 times 3 times x. Here I can rewrite this as negative 1 times x, and 2 times negative 1, I know it's just negative 2. So I can rewrite this as 3 times x squared plus 6x plus negative 1x plus negative 2. And I notice these two pieces are like terms, so I can add them, 3x squared plus, add the coefficients, 6 plus negative 1 times x plus negative 2. So I get 3x squared plus 6 plus negative 1 is 5x plus negative 2, which I can also write as 3x squared plus 5x minus 2. So, even though the distributive property only talks about distributing one thing to different pieces in a polynomial. We can distribute, if that one thing is a polynomial itself, we can distribute that polynomial to each piece, and then in the next step we can distribute each piece into that polynomial. So through 2 steps we can actually end up multiplying things that are not monomials. And you'll notice what actually ended up happening here. We ended up multiplying x times 3x. X times 3x. We ended up multiplying 2 times 3x. So 2 times 3x. We ended up multiplying x times negative 1. X times negative 1. And then we ended up multiplying 2 times negative 1. 2 times negative 1. So you can see what ended up happening here is we ended up distributing x to each piece and then 2 to each piece. In a sense, what ended up happening here is we ended up multiplying every term in the first polynomial by every term in the second polynomial. So it looks like there's a pattern here, perhaps. Let's try one more example and see if that pattern keeps up. And let's make this example even a little bit longer and more complicated. So let's do x minus 2y times x squared plus 2xy minus 3y squared. Okay, again, for my first step, I'm going to go ahead and rewrite all the subtraction as addition. So I'm going to rewrite this as x plus negative 2y times x squared plus 2xy plus negative 3y squared. Okay, make sure that square is really clear. Now, I'm going to use the distributive property just like I did before. I'm going to take this whole binomial here and I'm going to distribute it to each piece. So what am I going to get in that instance? I'm going to get x plus negative 2y times x squared plus x plus negative 2y times 2xy plus x plus negative 2y times negative 3y squared. Okay, that's helped me break it down in part, but I want to get rid of the rest of these parentheses, so I could do that by distributing the x squared to each piece here, the 2xy to each piece here, and the negative 3y squared to each piece here. So what I end up with is x times x squared plus negative 2y times x squared plus x times 2xy plus negative 2y times 2xy plus x times negative 3y squared plus negative 2y times 3y squared. Kind of ran out of room here, so let's write it here. Plus negative 2y times negative 3y squared. Okay, now we just need to simplify each piece and rearrange and combine like terms. So x times x squared I know is x cubed. Negative 2y times x squared I can write as negative 2x squared y, because I can just reorder the multiplication. X times 2xy I can write as 2 times x, which is x squared times y, plus negative 2y times 2xy, I can multiply the negative 2 times the 2 to get negative 4. The x is by itself, and the y times the y is y squared. X times negative 3y squared I can write as negative 3xy squared, just by reordering. And Negative 2y times negative 3y squared. Well, the negative 2 times the negative 3 is the positive 6, and y times y squared is y cubed. Now I just need to ask myself, do I have any like terms that I could combine? Well, this is my only x cubed. I don't see any other x cubes. This is my only y cubed. I don't see any more of those. Let me look at the terms in the middle. I have an x squared y piece, and here I have another x squared y piece. So these two can be combined. I have a negative 4xy squared, and I have a negative 3xy squared. So these two could be combined. So I can write x cubed, stays the same, plus negative 2 plus 2 x squared y. That's going to give me a negative 2 plus 2 x squared y, which I know is equal to 0. So that's going to go away, because this whole term will be equal to 0. And I've got a negative 4 plus negative 3 xy squared, so I know that's going to equal negative 7. And I still have my plus 6y cubed. So I'm going to get x cubed plus 0, which I can leave out because adding 0 doesn't change things, plus negative 7xy squared plus 6y cubed. So I'm done. I know that I can also write this as x cubed minus 7xy squared plus 6y cubed. Either answer is fine, because they both mean the same thing. So again, we notice, what is the general pattern here? Well, again, just as we noticed before, we notice that we end up multiplying x times x squared, right here. And then x times 2xy, right here. And then x times negative 3y squared, right here. And then we end up multiplying negative 2y times x, right here. And then negative 2y times 2xy, right here. And then negative 2 times negative 3y squared, right here. So we notice that what the general pattern is, we must multiply every term in the first polynomial by every term in the second polynomial. And you notice it doesn't really matter in what order we do that. We just need to be sure that every single term in the first polynomial gets multiplied by every single term in the second polynomial, and that all of those products get added together, and then we simplify what's left. You may have learned other techniques in other classes where they talk about the FOIL method and other methods of multiplying polynomials. All of those methods are really just one particular case, one special version of this. I personally think it's easier if you can just think about this one fundamental idea. If you look at the distributive property and you use it to multiply a bunch of different polynomials together, you'll see that what you always end up doing is you just end up multiplying every single term in the first polynomial by every single term in the second polynomial. And how you choose to do that doesn't really matter, as long as you're sure that you pair up every single set of terms. Every single set of terms that you can get by taking one from the first polynomial and one from the second. As long as you check that you've gotten all the possible pairs, then you can multiply them, the pairs, and then add the results, simplify what you get, and you'll get the same answer. One note of caution. Mistakes I see really often when students are doing these problems, I would say be sure to change all subtraction to addition. Technically, if we don't do that, we can't use a lot of the techniques we're using. You'll notice sometimes we get sloppy when we write things, and we will just go on and treat subtraction like it's addition without actually rewriting it, just keeping the idea in our head. But that's a bit dangerous because one of the mistakes I see students make an awful lot is when you do that, it's easy to lose the negative sign or put it in the wrong place or forget that it belongs with a particular number. You'll notice that negative sign always belongs to the number or the variable that follows it. So when we rewrite all our subtraction as adding a negative, we correctly put that negative sign with the piece where it belongs. So be sure, even if you don't listen to my advice and rewrite all subtraction as addition, be sure that you keep the negative sign with the correct term. Keep the negative sign with the correct term. Right? And what's the correct term? It's the one that comes after the negative sign is the one that should take it. So when we reorder stuff in an equation, in a polynomial, we always want to be sure that that negative sign travels with the term that comes immediately after it. And we want to be sure that we don't lose track of it. That's a very common mistake that students make all through this course and other courses. Really be careful, keep careful track of those negative signs. So that's it. We've talked about all of the major patterns and all of the major techniques we'll need in order to be able to simplify polynomials, to add them, to subtract them, and to multiply them. So you should be all set to do the homework on this section, adding, subtracting, multiplying, and simplifying polynomials on your own.